Okay, so we're continuing on with chapter 4, which is finally introducing the main object of study in linear algebra, which is vector spaces. Now, this section is on linearly independent sets and bases, and basically just bringing more. It's just this whole chapter is generalizing what we learned about Rn, the real numbers in n dimensions, to abstract vector spaces, which was defined in 4.1. Okay. So I've already read through some of this, but an index set of vectors is said to be linearly independent if the linear combination of those vectors, the equation of some linear combination of the vectors equaling 0 only has the case where the solution is satisfied by the coefficients being 0. Okay, if there's a non-trivial solution, then they're linearly dependent. A set containing a single vector v is linearly independent if and only if v is not equal to 0. Also, a set of two vectors is linearly dependent if and only if one of the vectors is a multiple of the other. Okay. All right. So theorem 4 says an index set of two or more vectors with v1 not equal to 0 is linearly dependent if and only if some vj with j greater than 1 is a linear combination of the preceding vectors. The main difference between linear dependence in Rn and a general vector space is that when the vectors are not n tuples, the homogeneous equation usually cannot be written as a system of n linear equations. That is, vectors cannot be made into the columns of a matrix A in order to study the equation Ax equals to 0. We must rely instead on the definition of linear dependence and on theorem 4. Okay, here's an example. So we have these polynomials. So the polynomial 1, the polynomial t, and the polynomial 4 minus t. And it's linearly dependent because P3 can be written as a linear combination of P1 and P2. Sine t and cos t are linearly independent in the set of continuous functions on the closed interval 0, 1. Because sine t and cos t are not multiples of one another as vectors. There is no scalar c such that cos t equals c sine t. All right, that's great. However, sine t, cos t, and 2 sine t is linearly dependent because the identity for half angle or whatever. Okay. Let H be, definition. Let H be a subspace of a vector space V. A set of vectors B in V is a basis for H if B is a linearly independent set and the subspace spanned by B coincides with H. That is, H is equal to the span of B. Okay, that's pretty, all this stuff is just saying the same definitions kind of that we already had. The definition of a basis applies to the case when H equals V. Thus, a basis of V is a linearly independent set that spans V. Observe that when H is not equal to V, condition 2 includes the requirement that each of the vectors in B must belong to H, because span B contains every element of B. All right. Let A be an invertible n by n matrix. Then the columns of A form a basis for Rn because they are linearly independent and they span Rn by the invertible matrix theorem. Okay, that's a simple example. Let E1 to En be the columns of the n by n identity matrix. The set of columns is called the standard basis for Rn. Okay, example 5. Determine if these vectors are a basis. Since there are exactly 3 vectors here in R3, we can use several methods to determine if the matrix is invertible. For instance, row replacement reveals that A has 3 pivot columns, thus A is invertible. as an example 3, the columns of A form a basis for R3. Let S equal to this. Verify that S is a basis for the polynomials of degree n. This basis is called the standard basis for Pn. Certainly S spans Pn. To show that S is linearly independent, suppose that C0, Cn satisfy the non-trivial. This means that the polynomial on the left has the same values as the zero polynomial on the right. A fundamental theorem in algebra says that the only polynomial in Pn with more than n zeros is the zero polynomial. That is, equation 2 holds for all t only if C0, if the constants are all zero. This proves that S is linearly independent because, and hence is a basis for Pn. Okay. Pn seems very interesting to study. The fact that it's a vector space is pretty cool. Problems involving linear independence and spanning in Pn are handled best by a technique to be discussed in 4.4. Okay. The spanning set theorem. As we will see, a basis is an efficient spanning set that contains no unnecessary vectors. In fact, a basis can be constructed from a spanning set by discarding unneeded vectors. Okay, let these three vectors and H be the span of a. Note that we can write the third vector as a linear combination of the first and second. Now, and then show that the span of the 3 is equal to the span of the first 2. Every vector in span v1, v2 belongs to H because because H was defined as the span of all 3, and you just set it equal to 0. Now let X be any vector in H. Say X equal to C1, V1, C2, V2, C3, V3. And since V3 is equal to 5V1 plus 3V2, we can just substitute that in for the thing, and it all works out. Okay, so here's the theorem. Let S be a set of vectors in a vector space, and let H be the span of those vectors. If one of the vectors in S, say Vk, is a linear combination of the remaining vectors in S, then the set formed from S by removing Vk still spans H. If H is not equal to the 0 subspace, some subset of S is a basis for H. I really don't quite understand that second condition. Okay, there's the proof. By rearranging the list of vectors in S if necessary, we may suppose that Vp is a linear combination of V1. Okay. Given any x in H, we may write substituting, and then okay. So this procedure is that you explicitly write out the linear dependence relation, then you write out the definition of an arbitrary element in a vector space, and then you substitute the linearly dependent one in for that, and you can show that you can just remove that vector from the spanning set. Okay, if the original spanning set S is linearly independent, then it already is a basis for H. Otherwise, one of the vectors in S depends on the others and can be deleted by part A. So long as there are 2 or more vectors in the spanning set, we can repeat this process until the spanning set is linearly independent and hence is a basis for H. If the spanning set is eventually reduced to 1 vector, that vector will be non-zero and hence linearly independent because H is not equal to the 0 vector, or the 0 subspace. Okay. Bases for the null space, column space, and row space. We already know how to find vectors that span the null space of a matrix A. The discussion in 4.2 pointed out that our our methods always produce a linearly independent set when null A contains non-zero vectors. So in this case, that method produces a basis for the null space. The next two examples describe a simple algorithm for finding a basis of the column space. Okay. Each non-pivot column of B is a linear combination of the pivot columns. By the spanning set theorem, we may discard B2 and B4, and B1, B3, and B5 will still span the column space. Since B1 is not equal to 0 and no vector in S, since B1 is not equal to 0 and no vector in S is a linear combination of the vectors that precede it, S is linearly independent. Thus, S is a basis. Okay, so because there's no linear dependence relation, it's independent, and since it's independent, then it spans the column space. Okay. What about a matrix A that is not in reduced echelon form? Recall that any linear dependence relationship among the columns of A can be expressed in the form of AX equal to 0, where X is a column of weights. If some columns are not involved in a particular dependence relation, then their weights are 0. When A is row reduced to a matrix B, the columns of B are often totally different from the columns of A. However, the equations have exactly the same set of solutions. The columns of A have exactly the same linear dependence relationships as the columns of B, where B is what, the row reduced? Yeah, the row reduced. It can be shown that the matrix is row equivalent to the matrix B, this one. Oh, okay, so we can expect that the linear dependence relationships are exactly the same. That's interesting. A2 is equal to 4. Okay. All right. Check that this is the case. Thus, we may discard A2 and A4 when selecting a minimal spanning set for call A. In fact, A1, A3, A5 must be linearly independent because any dependence relationship among them would imply a linear dependence relationship among B1, B3, B5. But we know that B1, B3, B5 is a linearly independent set. Thus, A1, A3, A5 is a basis for call A. The columns we have used for this basis are the pivot columns of A. The pivot columns of a matrix A form a basis for call A. Okay, the proof. Let B be a reduced echelon form of A. The set of pivot columns of B is linearly independent, for no vector in the set is a linear combination of the vectors that precede it. Since A is row equivalent to B, the pivot columns of A are linearly independent as well. So that's sort of where I have a gap in my understanding. Since A is row equivalent to B, the pivot columns of A are linearly independent as well. Because any linear dependence relation among the columns of A corresponds to a linear dependence relationship among the columns of B. For this same reason, every non-pivot column of A is a linear combination of the pivot columns of A. Thus, the non-pivot columns of A may be discarded from the spanning set for call A. By the spanning set theorem, this leaves the pivot columns of A as a basis for call A. Okay. The pivot columns of a matrix A are evident when A has been reduced only to echelon form, but be careful to use the pivot columns of A itself for the basis of call A. row operation. So this is what, yeah, row operations can change the column space of a matrix. The columns of an echelon matrix form B of A are often not in the column space of A. For instance, the columns of a matrix B in example 8 will have all zeros in their last entry. Right, but there's not zeros here. So they cannot span the column space of matrix A. In contrast, the following theorem establishes that row reduction does not change the row space of a matrix. Yeah. If two matrices A and B are row equivalent, then their row spaces are the same. If B is an echelon form, the non-zero rows of B form a basis for the row space of A and for B. Okay, yeah. So the proof is, if B is obtained from A by row operations, the rows of B are linear combinations of the rows of A. Yeah, okay. It follows that any linear combination of the rows of B is automatically a linear combination of the rows of A. Thus, the row space of B is contained in the row space of A. Since row operations are reversible, the same argument shows that the row space of A is a subset of the row space of B. So the two row spaces are the same. Okay, that makes sense. If B is an echelon form, its non-zero rows are linearly independent because no non-zero row is a linear combination of the non-zero rows below it. Right, because all the pivots, yeah. Thus, the non-zero rows of B form a basis of the row space of B and A. All right, example 10, find a basis for the row space. Okay, so they reduce it, and then you just take these first three. Okay, we're almost done with the notes. All right, two views of a basis. When the spanning set theorem is used, the deletion of vectors from a spanning set must stop when the set becomes linearly independent. If an additional vector is deleted, it will not be a linear combination of the remaining vectors. And hence the smaller set will no longer span V. Thus, a basis is a spanning set that is as small as possible. A basis is also a linearly independent set that is as large as possible. If S is a basis for V, and if S is enlarged by one vector, say W, from V, then the new set cannot be linearly independent because S spans V, and therefore W is a linear combination of the elements of S. All right, practice problems. All right, the practice problems. Determine if V1, V2 is a basis for R3. It has to be no and no. Right? Because the first one, this can't be a basis for R3 because first off, you only have two vectors. There's no way to span R3 with two vectors. And then it can't be a basis for R2 because the dimension's not right. Those vectors are in R3, so that doesn't make sense either. Okay, problem 2 is find a basis for the subspace W. Okay, so let's just do this. Okay, we can comment this out. Okay. All right, let's just do this directly. All right. So if we ref A, we get this. And so we have pivots on the first and second column. So V1 and V2 are the okay. So here, find a basis for the subspace W spanned by. So this is just going to be the set V1, V2. Problem 3. Every vector in H is a linear combination of V1 and V2. Is V1, V2 a basis for H? And that's just going to be no, because the span of V1, V2 is bigger than H, meaning that there are combinations that you can reach from these two vectors that are not in H. So, okay. Okay, so let V and W be vector spaces and let T from V to W and U from V to W be linear transformations. Let V1, hold on. Okay, let T and U be linear transformations, and let V1 of VP be a basis for V. If T Vj equals U Vj for every value of j between 1 and p, show that Tx is equal to Ux for every vector in V. All right, this one's really good. I'll be right back. Let's see if this works. There we go. I gotta do transform. What is it? Is it just rotate? All right. Okay. We can now, hold on. We can now do the problem. Okay, so the problem is T, U are maps from V to W. And V1, VP, basis for V. Then we have that T VI is equal to U VI for all I. Now the problem is show that TX is equal to UX for all X. Okay, so the trick here is to note that since V1 to VP is a basis, so since V1 VP basis of V, then an arbitrary vec in V can be written as a linear comm of basis vecs. So we can write X is equal to the sum of CI VI. Okay. So now we take T of X. So T of X is going to be equal to T of the sum of CI VI. Okay, hey, let me see if I can do this. I'm trying to see if I can. If I can maybe get the shadow out of it. It's a little better. Okay, I also don't love this. Okay, that seems pretty good. Okay, so then this is going to be equal to, so if we have, T of C1 V1 plus C2 V2 dot 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 C P V, plus VP. And this is going to be equal to, by the definition of linearity, uh, T times C1 V1 plus T C2 V2 dot dot dot. So this is going to be equal to the sum of T of CI VI. Then this, since it's still linear, you can pull out the constants. So you're going to get this equal the sum of CI T VI. But then since we know, since T VI is equal to U VI for all I, we can replace it as CI U VI. But then we can just undo the definition of linear transformation, which is equal to U of the sum CI VI. But this is equal to U of X. Therefore, they agree on everything. Okay, so there we go. So that's one of the nice proofs in the book. Okay, so let's just go back to reading the problems. This is in echelon form, and there's 3 pivots, so this is spanning. This is a basis. This one is not, because there's a whole set of non-trivial solutions to the homogeneous equation. We're going to skip those, skip these. Okay, find bases for the null spaces of the matrices. Okay, so these, we've done so many of these. Here's what you do. You take the RREF, you do the reduced row echelon form of this. Then you're probably going to have like a 0 down here, or you're going to have a couple of non-pivot columns. And so those are going to be the free variables. And then you write the non-free variables in terms of the free variables. And then the vectors that are used in that expression are the basis of the null space. Find a basis for the set of vectors in R3 in the plane x plus 4y minus 5z. Okay, so problem 11. Find a basis for vectors in R3 in the plane x plus 4y minus 5z equal to 0. Okay, now the thing about this problem is that you need to recognize that what this means is, like, if we were to treat it like a matrix, we would have 1, 4, minus 5, and then 0. So this is the augmented. So now if we were to just take 1, 4, minus 5 times x, y, z, we would get, equal to 0. This is the same thing. We're just rewriting it in different ways. But the thing to notice is that for finding a basis, what we're really finding is, if this is A, then we're trying to find null of A, because we're trying to find a basis for the vectors here that satisfy the equation. So we're trying to find the null space. Okay, so the way that we're going to do that is we are going to write x is equal to minus 4y plus 5z. Okay, so now we can write this equation as our minus 4y plus 5z y z. So we've written our equations in terms of a vector. So now this is equal to y times minus 4, 1, 0 plus z times 5, 0, 1. And so then these are the basis. Let me get my sunglasses. Okay. So what's the next problem? I'm going to switch back over. All right. So we just did 11. 12 is going to be the same thing. It's going to be, you just turn this into a homogeneous equation. So if you get 5x minus y is equal to 0, then you can write x in terms of y. So you're going to get x is equal to 1/5 y. And then so then you can rewrite that as y 1/5 y as a vector is equal to y times 1/5 and 1. So yeah, okay. So it's the same process. Find the null space of that thing, of the homogeneous equation corresponding to that. Okay. In 13 and 14, assume that A is row equivalent to B. Find the bases for the null space, column space, and row space. Okay, so for the null space, okay, so let's just write that out. So find null A, col A, and row A. So, okay, so the col A is going to be the first two columns here because they're the pivots. For the row space, it's going to be the first two rows of either, because by theorem 7, if A and B are row equivalent, then their row spaces are the same. And if B is in echelon form, then the non-zero rows of B form a basis for both A and B, for the row space of A and B. So since B is in echelon form, then we can take either these two or these two. Okay, now the null space, you do the same process as before. You write it in you write the solutions in parametric vector form or whatever, and then you just take those vectors in that form as your bases, and that'll be a basis for the null space. Find a basis. Yeah, I don't really want to do those. Those are boring. Let V1, V2, V3, and H the span. It can be verified that use this information to find a basis for H. So, so what we're going to do is we're going to solve for V3. So add V3 3v3 to the other side and then divide this. So then you're going to get 1/3 times this is, so then what you do is you write an arbitrary element of x equal to, c1 times v1 plus c2 times v2 times c3 times v3. And then you replace the v3 with the 1/3 times this. And then you can show that these two are a basis for h. Okay. This looks like the exact same problem. All right, true, false. True, falses are good. Okay. A single vector by itself is linearly dependent. That's false. 22. A linearly independent set in a subspace H. A linearly independent set in a subspace H is a basis for H. That is not true. False. It's not guaranteed to span H. If H is equal to the span of B1, BP, then BP is a basis for H. No, because it's not necessarily linearly independent. False. B1 to BP, not guaranteed to be in depth. Okay, 24. If a finite set S of non-zero vectors spans a vector space, then some set of S is a basis for V. That is true. 25. The columns of an invertible n by n matrix form a basis for Rn. Yeah. Since it's invertible, they're linearly independent, and if they're linearly independent, then yeah. So true. A basis is a linearly independent set that is as large as possible. I didn't really like that thing at the end there, but I know it's true because if you just go to the notes, it says a basis is also a linearly independent set that is as large as possible. Okay, I get it. Never mind. Yeah, that makes sense. Okay. Yeah, so that one's true. 26 is true. 27. A basis is a spanning set that is as large as possible. No, that's false. The standard method for producing a spanning set for the null space sometimes fails to produce a basis. That's false. Though I didn't understand that thing about them being non-zero or something like that. I don't know what happens in the case that there's... All right. In some cases, the linear dependence relations among the columns of a matrix can be affected by certain elementary row operations. That's false. If B is an echelon form of A, then the pivot columns of B form a basis for the column space of A. That's false. The row operations are not guaranteed to preserve column space. Okay, 31. Row operations preserve the linear dependence relations among the rows of A. That is true. That's true. Because row operations are just linear combinations. So, yeah. 32. If A and B are row equivalent, then their row spaces are the same. True. Okay, time to double check. Hello. So, Ito. All right. We're just going to wait on this. Wow. Okay, let's see what the next problem is. Suppose that R4 is equal to the span of V1 to V4. Explain why V1 to V4 is a basis. Okay. This is a good question. Why? I mean, the naive answer that I want to give is that that they must be linearly independent. Okay, to be a basis, you need to span the set and you need to be linearly independent. So it spans it because we're given that. But now, the fact that there's 4 vectors in R4, yeah, I like what I want to say is just you need 4 independent vectors to span R4. All right, wait, let's double check these answers now. Okay, so false, false, false. Okay. True, true, true. False, false. False, false, false. 30, false. 31, true. 32, true. Okay, good. We got all those right. Okay, I want to know what the correct way to answer this is. Okay, wait. So what we need to show we basically need to show that that linear combinations of this set equaling 0 only has the trivial solution. All right, I'm gonna cheat. My answer is that it's because the only way for 4 vectors to span R4 is that they're all independent. But I don't think that's the most concise way to. I'm doing good, man. Trying to get through this section because I have a bunch of differential equations to do, and that's more fun because differential equations I can do on the whiteboard. Okay. Any spanning list of exactly 4 vectors must be linearly independent. Because the dimension of R4 is 4. Yeah, okay. If they were linearly dependent, one of them could be removed, and it would still span R4. Impossible since no set of fewer than 4 vectors can span a 4-dimensional. Okay, so it was what I said. Let B be a linearly independent set in Rn. Explain why B must be a base. Okay, this is the exact same. This is the exact same as here. It's just generalized to n dimensions. So the same argument holds. All right. V1, V2. And let H be the set of vectors in R3 whose second and third entries are equal. Then every vector in H has a unique expansion as a linear combination. Okay, so what I'm guessing is that no, but what I want to do, here's what I'm going to do. Okay, wait, we can just write this out by hand. So it's going to be 1, 0, 0, 0, 1, 1, 1, 1, 0. Let me just write that out. 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay, so if we do A is equal to 1, 0, 0, 0, 1, 1, 1, 1, 0, and then we do the rank of A. So this is a linearly independent set. So the thing is, though, that H represents a two-dimensional subspace. So V1, V2, V3 is not a basis because their span is bigger than H. There are elements in this span that are not in H. Okay, in the vector space of all real valued functions, find a basis for the subspace spanned by sine t, sine 2t, sine t, cos t. So I think you can just remove this, right? Alternatively, you could just remove this one. Let's see if that's right. I'm pretty sure that that's right. Because you use that half angle identity to delete the... You basically create a linear combination. All right. Let V be a vector space of functions that describe the vibration of a mass spring system. Find a basis for V. We should probably do that one. Okay. Let's just see. Were we right? Yeah, so you just take the first two. That's what I thought. Okay. So we need refer to exercise 19 and 4.1. Okay. So what is it saying? It's saying find a basis for the vector space of functions that describe the vibration of a mass spring system. Okay, so we need a linearly independent set. Okay, so I mean, like, just recognize that this is a linear combination, right? First off, you can't write sine as a multiple of cos and vice versa. And then this just looks like a dot product. Actually, is dot product the right name? No. But what I'm saying is that you have a coefficient times some vector plus a coefficient times some vector. So what I would say is that the basis in 37 is um, is um, is the vector cos omega t and sine omega t. And yeah, okay. So we're just gonna do this. And this. Okay, we can keep going. All right, the circuit in the figure consists of a resistor, an inductor, a capacitor, and an initial voltage source. Let B equal 2 over, or R over 2L, and suppose RLC have been selected so that B equals 1 over... This is done, for instance, when the circuit is used in a voltmeter. Let V of T be the voltage in volts at time t measured across the capacitor. It can be shown that V is in the null space of H of the linear transformation that maps V of T into L V double prime plus R V prime plus 1 over C V T. And H consists of all functions of the form Ooh, this is a tough problem. This is a pretty hard problem. What? H consists of all functions of the form v of t is equal to e to the minus bt times c1 plus c2t. This is one of those ones you're like, what do I even do? It can be shown that v is in the null space of H. But I think that isn't this a lot of like if we expand this out and we distribute this, we get c1 times e to the minus bt plus c2t times e to the minus bt. And I think that you just take e to the minus bt and te to the minus bt as your basis, right? So I'm pretty sure for 38, the basis of H is just e to the minus bt and te to the minus bt. So it's more wordy than anything, but because they're not asking you to show that v is, so H is the null space. So you're trying to find a basis of a null space. I don't know. I need some help on this one. Well, let me take a second just to like think about it. So H is the null space. So if we were to convert, so if we take C1 e to the minus bt, all right, so here we'll write this out. So if we have plus c2t e to the minus bt, and then we're going to take this, we're going to compute t of this. So we need to take the first derivative of this, which is, so if this is equal to v of t, then we want to compute t of v. So so v prime of t is equal to, I think it's going to be minus b c1 e to the minus bt plus so this we need a product rule. So c2t e to the minus bt, this becomes prime is equal to c2 e to the minus bt plus minus b c2 t e to the minus bt. Is that correct? Oh, but then we have to do a second derivative. This is going to get so messy. Oh, I don't really want to do all that. All right, let's just see if this is the basis, because it seems like that's the basis. I just don't know why they went into all this stuff about B is equal to R over 2L and stuff. Oh, nice. Okay, so we did get it right. The convenient choice is the two functions you get by taking the two independent polynomial parts, 1 and t, multiplied by a common factor. Okay, that's what I thought. So it was more of a problem to make sure that you're like awake. You know, they're trying to throw in a bunch of gibberish to see if they can throw you off the trail. All right. Show that every basis for Rn must contain exactly n vectors. Let's do a v1 of vk. Set of k vectors in Rn with k is less than n. Use a basis from section 1.4 to explain why S cannot be a basis for Rn. Let's go to section 1.4. So what are we trying to show? We're trying to show that I don't know what the. I think it's more so that v1 to vk cannot span Rn because you need n vectors to. Okay, whatever. Those ones, I don't know what they're trying to get me to do, but you can't use less than n vectors to span dimension n. And then same here, there must be a dependence relation because once you have a set of n vectors that are linearly independent that form a basis of Rn, then any other vector you add to your set S is going to be dependent on the previous ones. So then you can just remove it and it spans the same space. Exercises 41 and 42 reveal an important connection between linear independence and linear transformations and provide practice using the definition of linear dependence. Let V and W be vector spaces and T from V to W be a linear map. Let V1 of VP be a subset of V. Okay, so let's just write those out. So we have T from V to W, linear map. And we have V1 to VP as elements of V. All right, I'll be right back. Okay. So, all right, so let's see, what are the problems? Show that if V1 to VP is linearly dependent, then the set of images is dependent. Ooh. I think what you do is, okay, let's say P is equal to some linear combination of V1 to VP minus 1. Then you, okay, this is a good one. If V1 to VP dependent, then T V1 T VP is dependent in W. This fact shows that if a linear transformation maps a set onto a linearly independent set, then the original set is linearly independent too, because it cannot. That's sweet. That's a great, it's a good one. All right. So, all right, if V1 to VP dependent, then, and I think we can say without loss of generality, VP is equal to the sum of CI VI for, I up to, for I in 1 to P minus 1. Okay, so we're writing this as a linear combination of the preceding vectors. So then if we do, so then if we take T of VI, then we can replace for all I is equal to the set, T V1, and then we're going to get here T of the sum of CI VI. But this is going to be equal to the sum of CI times T VI. And so therefore, wait. This is, yeah. So this is all you really have to do. This is the whole proof, is that since you've done this with, since we can write T of VP equal to the sum of CI T VI for all I in 1 to P minus 1, then it is dependent. Yeah, that's it. It is dependent, meaning the set Ti or T of Vi is dependent. Okay. Yeah, VP is equal to the. So alternatively, we could have written this as like sum, or not sum, sorry, set of T1, V1, T, V2, T, VP. But we can substitute in VP for this sum. And I guess we should save like for I and 1 to P minus 1. Okay, so that's that. That was a good proof. I like those ones like that where you really have to apply the definition. Suppose that T is a 1-to-1 transformation. So that T of U equals T of V implies that U is equal to V. show that if the set of images is linearly dependent, then this shows that a one-to-one linear transformation maps a linearly independent set onto a linearly independent set. Okay, so for this is 41, and this is going to be 42. So suppose T is 1, 2, 1. Prove if T of V1, or yeah, the set T of Vi is dependent, then the original set Vi is dependent. All right. Time to get proven. All right, so suppose T is 1-to-1. Prove that if the set of vectors T of Vi is dependent, then the set Vi is dependent. Okay, so that means that we can write we can write T of Vp equal to the sum of Ci T Vi for I in 1 to P minus 1. So this is just saying that this is just the definition of linear dependence. We can see that we can write one of the images as a linear combination of the other images. Okay, so now we need to show, now we want to show that Vp is equal to a sum of Ci Vi I in 1 to P minus 1. Okay, so but what this is equal to is the sum of, first we can do this TCI VI, and this is, because linear map. Wait, but I don't know where we're going to use the 1-to-1 thing. Okay, but what I would be inclined to do after is just do this. But I don't know where the one-to-oneness came in. I think I'm going to ask ChatGPT to answer these two. Let's see what just because these are like the theory questions that you really don't want to have any misunderstandings of. Okay, so suppose is linear dependent, then the scalars, there exist scalars, not all 0. Apply the Okay, so this is how they did it. Yeah, this is actually even cleaner than how I did it. by linearity, okay. And injectivity of yeah, so this is where we use the injectivity. Wait, what? Okay, injectivity means T of U equal to T of V implies that U is equal to V. Oh, so we're okay, so wait, so injectivity is T of U is equal to T of V implies U equal to V. So if T of V equal to 0, then and T of 0 equals 0, then T of V is equal to, or then V is equal to 0. Okay, that makes sense. Okay, so so in here we're gonna change this so that by injectivity, if T of V is equal to 0 and T of 0 equals 0, then V is equal to 0. But since V equal to is equal to a sum of A, I, V, I, but the AI are non-zero, then there is a dependence. That was the best one yet. Let's see. That one, so 42 and 41 and 42, and there was a couple other good ones in here. Okay, let's see. We have 3 problems left. Consider 1 plus t squared and 1 minus t squared. Is P1, P2 a linearly independent set? That's an interesting question. Yeah, they have to be because because when you only have 2, you can just check if you can write them as a scalar multiple, and there's no way to write them as a scalar multiple. So 43, yes, they are independent. Neither is a scalar multiple of the other. That one was easy. Consider the polynomial. Well, let's just check our answer, but almost like I'm like 99% on that one. That one's pretty easy. Consider the polynomials p1t. Okay, like p1 plus t, 1 minus t, and then p3 equals to 2. Oh, by inspection, write a linear dependence relation. Okay, so you just take p1 plus p2. And then, okay, so the first one is the dependence relation for 44 is p1 plus p2 is equal to p3. So that means we should be able to just remove p3, right? So then our basis is going to be p1, p2. Yes. Oh, yeah, it is. Okay. And then for my basis, I just wrote p1 and p2. Okay. Let V be a vector space that contains a linearly independent set u1 to u4. Describe how to construct a set of vectors v1 to v4 in V. Wait, what? Describe how to construct a set of vectors v1 to v4 in V such that v1, v3. I think you just add a couple of degenerate columns, right? So, like, let's just say v2 is equal to v1 plus v3, and v4 is equal to v1 minus v3. I'll just write that out, but I'm pretty sure that that's v2. Oh, okay. So wait. So you let u1 equal v1, or let v1 equal u1, and v3 equal u3. Then v2 is equal to v1 plus v3, and v4 is equal to v1 minus v3. Okay, so I'm pretty sure that you can just do that. Quick inspection shows that okay, so one non-trivial dependence. That's great. So since P3 is equal to P1 plus P2, the span is really just all combinations of P1. Okay, so that's great. We did that right. Last problem. What's the next section? It's coordinate systems, right? Yeah. Nice. Yeah, exactly. And then you just do plus and minus or something random. All right, that was easy. Okay, so that wraps up section 4.3, linearly independent sets and bases.